Hi, in this video I'll be presenting a separate proof for vector projections. I again have the two vectors u and v, and I'll be finding the projection of u onto v. This time I'm going to think of the vector u as having a component that's parallel to v plus a component that's perpendicular to v. So if a vector is parallel to v, I can write this as kv, where k is a real number, and w, where w is perpendicular to v, or in other words, orthogonal to v. So I have the equation u is equal to kv plus w, or w is equal to u minus kv. Since w is perpendicular to v, therefore w dot v is equal to 0, or u minus kv dot v is equal to 0, or u dot v, by the distributive property of dot products, minus kv dot v is equal to 0. Rearranging for k, I have k is equal to u dot v over v dot v. Now we know that for dot products, the two vectors v dot something else is equal to the magnitude of the first vector times the magnitude of the second vector cos of the angle between them. But the angle between two parallel vectors, or in this specific case, it's the same vector, is 0 degrees. So I have v squared. So I'm going to replace this with u dot v over the magnitude of v squared. However, we're trying to find the vector kv and not the scalar k, so we're going to multiply both sides by v. And we arrive at the vector projection equation. Now, this proof is interesting because it does not require casework, and it arrives you to the answer. But there's also a disadvantage of this proof, which is it's less intuitive than my other proof. Now there's a situation in my portfolio where you had to find the magnitude of the projection of a vector onto another, and finding the magnitude of this vector itself is more complicated than a simplification. So I'll be showing you how to simplify the magnitude of a projection. The magnitude of kv is equal to u dot v over the magnitude of v squared times v. I'm going to rewrite this. I'm going to move this magnitude here, so I have u dot v over the magnitude of v times v over the magnitude of v. Notice that this component here is v hat, or a unit vector v. So I'm going to write this as u dot v over the magnitude of v times v hat. Since v hat is a vector and u dot v over the magnitude of v is a scalar, I can separate this absolute value into u dot v over the magnitude of v times the magnitude of v hat, which is 1. So this is equal to the magnitude of u dot v over the magnitude of v, and I can simplify this into the magnitude of u dot v over the magnitude of v, which is simply just the magnitude of v. So this is the magnitude of the projection of u onto v, and you can see that finding this is much easier than finding the magnitude of this vector here. Next, I want to show you something cool with alcohol. I realized that when I rub some alcohol in my hands, like so, and I turn off the lights, and I light up, you can see that my hands go on fire. Very interesting. Let's put some more alcohol on my hands. This time it will hurt a bit more because I have more alcohol on my hands. Ouch! Thank you for watching.